we're going to take a look at congruence and similarity with transformations. So first we're going to talk about translations and rotations, which are going to be movements up, down, or to the side in the plane, and rotation being actually taking an object and rotating it around a point. So the first definition that's going to be really important is that a definition of isometry. So any rigid motion, so translation or rotation, that preserves length of a shape or distance is an isometry. A translation is a type of isometry because when I pick up an object and move it, I'm not changing the size or the actual shape. It's remaining the same. It's not being altered. Any function in the plane to itself that has a one-to-one correspondence is a transformation. So what does that mean? That means if I'm doing the same thing to every point on the shape, it's a transformation, whether it be reflecting, rotating, any of those things that maps one thing onto another. So if I've moved something in the coordinate plane, I can use a transformation to put it back on top of itself. Because transformations are functions, they have the same properties as functions. So a translation is a movement. It's a movement of motion that every point shifts, kind of like when they go down the slide. If a child starts at the top of the slide, they're going to end at the bottom of the slide. They've just moved location. Nothing else has changed. The child's size hasn't changed. The object they're on hasn't changed. It's just a clear movement. A figure and its image, when translated, are congruent. So again, we didn't change the size of something. We just move it. And the image of a line is a line parallel to it. So when I start talking about the image of a line, that's me kind of tracing the movement there like you have beside them on this slide. To construct the image of an object under a translation, we need to know what is the rule. How do I move from A to A prime? So when we're constructing these translation images, you can use a compass and straight edge, which again, last week as we spoke about, is kind of a dying art, and we can actually translate things. Most often though, we're going to use the coordinate plane and we're going to be able to just explain, I moved it 2 to the right or 2 to the left. Okay, so if I'm looking for AB under the translation from X to X prime, then this is what I'm moving. I'm actually moving a triangle. The image of each point on this dot paper could be obtained by shifting it 2 units down and 2 units to the right. And that's how I would obtain this over here. So 2 units down, 2 units to the right, and that's where that's coming from. If I'm looking at it in the coordinate plane, this is probably the first place to show your students a translation, and I would start with just showing like moving one way, up, down, or to the side, one thing. In the translation, we're adding 5 to X, which means we're going 5 to the right, and we're subtracting 2 from Y, which means we're going down 2. So I took this point B, went 5 to the right, down 2. Here's my new B. I took A, 5 to the right, down 2. Here's my new A. And then I do the same thing with C, and I connect the dots, and there's my shifted image. So really, you're just taking coordinates and completing the rule with the coordinates. In a translation within a coordinate system, we have these nice functions where I'm adding or subtracting a number to X and Y, and that's called the rule. We can write this symbolically as X comma Y, and then an arrow says moves to X plus some number, Y plus some number. So this is not the typical function that you're used to seeing in the form of Y equals. We're talking about something slightly different here. Here's an example. If you wanted to find the coordinates of the image of the vertices here of this quadrilateral, I'm taking everything here and I'm moving it 2 to the left and 4 up. So I'm going to have to do that within this example, is take every coordinate there and subtract 2 and add 4 to get my 4 new points. Once I have my 4 new points, I can then plot those 4 points and I get the translation here of what's been done. Again, if I want to look at a translation determined here, the translation is going to be moving the X coordinates 2 units to the left, and then the Y coordinate, we're going to go up 4, looking at the coordinate points compared to the beginning points. Now this time I'm not given the points, however it is in the coordinate plane, so I am able to actually locate the points. The biggest thing you're going to have to remind your students is that when you're looking at this, the prime is going to be the actual image after it's happened. So I'm actually going from the black triangle to the blue one. And that's going to be really important. So if I'm looking at this translation, point B moved up 1, 2, 3, 4, and it moved to the left 2. So that would be x minus 2, y plus 4 would describe that motion. Rotations can be a little harder to understand for students, especially at a younger age, because it's a turning of the object. So it's changing the orientation of the object, but it's not changing the size or the shape. So these are some examples of rotation. It's a good idea to have them draw it on a sheet of paper and then rotate the paper. Sometimes that's easier to really convey the idea of a rotation to students. So in isometries, coming back to us again, we're going to talk about isometries a lot. And a circle would be considered an isometry because I'm not changing the size of the circle when I rotate it. I'm not changing the shape of the circle when I rotate it. And so it remains the same. Now, what can be difficult is if I'm rotating about a point O, I have to maintain the distance from point O. So here I took this and I rotated it over about 90 degrees maybe, not quite 180. And that gives me a rotation. There are some special rotations, and that's anytime you go in a complete circle, you're going to get the same answer. So that's why we call it an identity transformation. A rotation of 180, we call it a half turn. And then that's going to connect to the idea of perpendicular lines. So when I use perpendicular lines, those are going to have the nice box showing they are perpendicular, but the slope of a perpendicular line is going to be the negative opposite or negative reciprocal of the other slope. So if my first line is b over a, my second line is negative a over b. So we're flipping the fraction and we're changing the sign. Two lines which are vertical are perpendicular if and only if when you multiply them together you get -1. And that's where the idea comes from of the negative opposite. So if I want to find the equation of a line that's going to be perpendicular, my first step is to take that line that's been solved for y to find the slope. So the slope of the line I'm given, 3x plus 5, has a slope of 3. The negative opposite is -1/3. For this line, I'm going to have -1/3 x, and then I have plus my y-intercept. I can plug in the x coordinates that I was given and solve for my y-intercept to get my final equation.